Our next speaker is Henning Paul, and Henning has been a hardware hacker since his childhood. Henning is here already with us. He gained interest in wireless communication only during his diploma and PhD studies in information technology at the University of Bremen. And having left academia for the industry a few years ago, Henning decided to intensify his free time activities on software-defined radio and is currently waiting for his amateur radio novice license examination to be finally able to transmit and not be restricted for receiving only. And the topic Henning is going to talk to us is about building a flexible, multi-antenna capable SDR using open source technology. Henning, the stage is yours. Please go ahead with your pre-recorded video.
Thank you very much for the kind introduction. My name is Henning Paul, and this is my second talk in this year's SDR Academy. And if you've seen the first talk, this was on SDR in scientific applications, in particular in communication technology. And this is more or less a follow-up talk to the earlier talk, but you will be able to understand it regardless of whether you heard the first talk or not. So in this talk, I would like to tell you a little bit on my current activities, my homebrew SDR. That's largely inspired by the scientific SDRs that I've used in my past. And I will also point out on what open source technology or open source projects one can today rely on to build one's owns their own hardware demonstrator, or software-defined radio, as it's called today. So let's start with the beginnings. Yeah, back then when I still was at university, I guess it was my last year as a researcher in the university, I was thinking on how could I build an affordable, not say cheap, non-real-time capable hardware demonstrator based on available technology. And my idea back then was to use a Raspberry Pi as a computing device and then equip this Raspberry Pi with a FIFO and an ADC, and then later hook this up to a modulator that would then be able to transmit arbitrary signals in non-real time, but at least arbitrary signals over 2.4 gigahertz transceiver, or in this case, transmitter. And the idea was then to maybe use this technology for wireless sensor networks, because this was my research topic at this time. And this is why I was trying to find a solution that is, say, costly, so not as costly, so that you would be able to send up a large number of these sensor nodes in order to do some cooperative communication between sensor nodes. This was a non-real-time system. I already mentioned that. That means you would fill the FIFO from the Raspberry Pi using SPI, and you would have the static RAM here on this board that would then be filled over SPI, and then we would then write out the memory contents over a digital to analog converter, and then output the signal then on these two SMB jacks, and then feed this signal into the modulator board, which looks like this. This is a modulator board using an ADRF 6720. This is a fully integrated modulator, which only needs a crystal as external part, and everything you need is inside the modulator, the PLL, the VCO, and the like. Just analog baseband in, RF out. This modulator has a frequency span, I guess, from around 400 megahertz to 2.8 gigahertz. So this was intended to be used with 2.4 gigahertz Wi-Fi frequencies. Yeah? If you see my previous talk, you'll know what I'm talking about. Yeah, and I actually managed to be able to transmit some signals over the setup. And for instance, here on the left, you see our lab. And you see the spectrum analyzer to the left, which shows the received spectrum of an OFDM frame that I transmitted using the setup, with the Raspberry Pi based baseband board and then the external modulator board. The idea was to use, say, a modified RTL SDR for reception. That's why I designed a receiver board with the counterpart to the modulator you've seen before. The receiver is the ADRF 6820, which is the matching receiver to the transmitter's 6720. And then I fed the baseband outputs into a plain, simple RTL SDR into the IQ inputs. And by doing so, I would basically get a 2.4 gigahertz RTL SDR. RTL SDR able to receive at 2.4 gigahertz ISM band frequency. So this was the idea. But then I shortly later abandoned the idea of this Raspberry Pi based system because after all, it's not real time. It's still offline processing. And this is why I had a look at other open source projects that were available at this time. And this is how I stumbled across the HackRF. And I guess you know the HackRF. It's a famous system. The schematics are available. And that's why I designed a digital controller board, which is software compatible to the HackRF. It's basically an HackRF clone using the same microcontroller. This NXP LPC series microcontroller as the original HackRF. And then I chose this modular design where you have the digital PCB here. And then this is the ADDA board. This was perf board in the beginning, and I later then made a proper design, 2-layer PCBs for the analog inputs and outputs. And this design used a MAX 5189 parallel DAC. This is a 20 megasample DAC with 8-bit parallel interface. And for ADC conversion, I used the ADC 1175, which is in Texas Instruments part. It's also 8 bits, 20 megasamples per second parallel interface. And I hooked this up to this digital board, digital HackRF compatible board. And instead of the CPLD that's used on the HackRF, I chose a discrete digital logic. So it's 74 VA, very, very high speed CMOS glue logic. You can see this here on the PCB. It's these SOIC 14 and 16 chips that basically do all the timing stuff, creating the enables and the gating the clocks and the like. If you know the HackRF's VHDL source code of the CPLD, you will know what I mean. It's just generating control signals. The analog part used a dual rail design. This is why I used the DC-DC converter, which converted the 4.5 volts you effectively get from the USB to plus 5.5 and minus 5.5 volts, and then I placed an LDO each in each rail to then generate clean plus minus 5 volts for the analog part with proper filtering, of course, because DC-DC converters a bit problematic. I forked the libHackRF, and I also forked the embedded software running on the microcontroller, and basically this was how I got operation with any software that supports HackRF was able to support my SDR. Let's just say it's a modified version of all the source code. And that's, I guess, one of the large benefits of open source software. You can just get the source code from GitHub, modify it to your needs, and then load it into your own homebrew design. And basically, you're standing on the shoulders of giants regarding the software that already exists out there. Here on this board, you see my SDR hooked up to a receiver board. This is now a VHF receiver. It's the ADRF 6806. It's unfortunately obsolete part by now. Means you won't be able to recreate this project on your own because you won't be able to buy the chip anymore. This is a VHF receiver from something like 50 megahertz to, I guess, 500 megahertz, and I used it to receive weather satellite, weather fax, using 130 something megahertz signals. Yeah, this worked quite well actually. So the setup here, but then I again abandoned this system to for something which was more powerful, and the reason to do so was the Pluto SDR. So HackRF was nice and cool. At the time it was new, but then later, I guess you all know the Pluto SDR, and which is cooler than the HackRF. And that's why I also switched from an HackRF clone, not a Pluto clone, but at least technology that was heavily inspired by the Pluto SDR. Means basically I move from an USB 2.0 solution to a solution with gigabit Ethernet, because I don't need to tell you this. One of the big drawbacks of the Pluto SDR, it only has USB 2.0. And in a lot of applications, you would like gigabit Ethernet interface better than this flaky USB interface. So this is why I chosen Zinc board, using basically the same system on chip part as the Pluto SDR does. Evaluation board from Digiland. It's the Cora Z7 evaluation board. And I hooked up this evaluation board to an external DAC. Sorry, not a DAC, an ADC. I hooked it up to an external ADC using this setup you see here with an adapter board and a flex cable. And then here you see this is the ADC board. And I was able to reuse a lot of blocks from the Pluto SDR, because Analog Devices has GPL'd their hardware design language HDL library. It's on GitHub, and this basically is a link here. If you get the slides, you can click onto it. You find all the blocks from the Pluto SDR there. You will find the decimator block there. You will find the DMA controller that's essential to get samples properly into your ZOC from the ADC. So it means by using all these GPL blocks, you are able to set up a system which is quite powerful with not too much effort actually. And what you see here in this picture here is now my receiver board hooked up to the same VHF receiver board you saw on the previous slide. It's a modular design. This is what I learned from my time at university. If you have a modular design, you can easily swap out transceivers for different bands. Let it be VHF, UHF, or even only operate in baseband, because you don't need an up converter because the ADC is fast enough. That's what the next slides will be all about. So means you're standing on the shoulders of giants. I can only repeat myself, because there is so much very high quality open source code out there that you can easily use. This is the current state of my SDR. You see here, I made a nice PCB here that I put on the my evaluation board. It has currently it's a 40 mega sample 12-bit ADC, and operating at 40 mega samples per second. And of course, what's nice is that there are pin-compatible ADCs with up to 105 mega samples per second and 14 bits. Of course, this one is, I guess, 95 euros plus tax for a single piece, so it's a bit pricey. This one here, I guess, is 20 euros, the one I'm currently using, but you could easily upgrade the system and then to get even more bandwidth. Of course, the bottleneck in this here is this gigabit Ethernet, because 1 gigabit is rather easily saturated, and you have to be aware that on the other side of the gigabit link, you have to process this data somehow. So it means real-time processing on the receiver side also needs to cope with the amount of data that's rushing through your gigabit Ethernet link. This is a dual channel ADC because you need it for IRQ, obviously. But of course, if you don't use it with an external modulator, you have two independent differential inputs here. Yeah, you see 4 SMB connectors because we have a differential input. There's a fully differential programmable gain amplifier here on this board that you can also set from via software, identically to how you would set the gain of the Pluto SDR. And what I also did, I wrote a kernel module to support this, my design. You can find it on my GitHub. The link is here. It's hidden in the text there. And what I also did, I modified the GR-IIO and the GR-Osmo SDR block sets. They are also on my GitHub to support this board. Means now I can use every GNU Radio application, including GQRX, to receive signals with my SDR, standing on the shoulders of giants. Yeah, now this is a block diagram on how the system looks like. We have, like I mentioned, this programmable gain amplifier here on the PCB, which can be controlled from the processor. This dual channel ADC. I have also integrated a mixer using direct digital synthesis. Means I can set the mixer frequencies in integer multiples of fs by 8. Means if you're running at 40 megasamples per second, I can set the mixer to 5, 10, 15, 20 megahertz. And then there's a decimator by a factor of 8, exactly the same decimator as in the Pluto SDR, which will then decimate your signals down and feed it over Ethernet into your PC. And yeah, what can you do with this setup? I have tried a little bit. This was a little bit silly, but it was a quick and dirty test that I did. I built 2 loop antennas. Yeah, I guess some of you may smirk about how my loop antennas look like. Basically, it's just pieces of coax with a crossover adapter here and a 2-to-1 balloon here, and the 20 megahertz low pass, 7th order Chebyshev low pass here, directly attached to it. But I basically built these 2 very cheap and very dirty, not only quick, but very dirty antennas here. And I just hung them on some piece of PVC pipe here, and I hooked them up to the inputs of my ADC. I set the gain to maximum, which is 20 dBs, what this programmable gain amplifier is able to do. And I set the mixer frequency to 5 megahertz. And this is the spectrum that I was obtaining. Here it's now shown in GNU Octave. Yeah? I've sampled into a file, and then I did some offline processing with GNU Octave. And you see a lot of QRM, means 80 meters is unusable. But there is some hope for 40 meters. And this is why we'll have a look at 40 meters on the next slide on how the signal looks like. And we now zoom in into the, before we zoom into the board, we will have a look at the cross correlation between these 2 signals to the 2 different channels. This figure here is the autocorrelation. See the auto power spectral density, to be precise, that is shown here, the spectra of the 2 input signals. Of course, there is the cross correlation time domain, and in frequency the counterpart is the cross power spectral density, the cross PSD. And this is shown here. So this basically shows us what do the 2 channels have in common. And you see a lot of QRM they have in common. But they also have in common some particular signals of interest, because you can see here, the beginning of the 40 meters band, that there are some interesting lines here, and this is the phase. Yeah, the auto PSD, auto power spectral density, has no phase information. It's just a power. The cross power spectral density has phase information, because it tells you something about how is the phase difference between the 2 signals that you have calculated the power spectral density of. And now we will zoom in into the 40 meter band and have a look at what we can see there. And now we get this figure here. Yeah, we zoomed into the band. We did some bit of filtering. So this is why we have the slopes here at the sides of the plot. Yeah, this is basically the slope of our decimation filter. decimation in GNU Octave only, not in the hardware. It's offline processing. And what I did was to detect the peaks in the cross power spectral density. Yeah? And these peaks are shown here with the circular markers. Each of those is some signal of interest. And what's particularly interesting here is in the plot down below here is the phase between these two signals. Means this plot tells us with what phase difference the two signals have been received. And you see here that the different stations obviously have been received with different phase angles. Because somehow, even if my setup was a bit, say, improvised, at least my two antennas received the signals somehow differently with a different phase. This cannot just be, it could be, say, just due to the different time difference of arrival, but this may also be that the field components are somehow different at these two antennas. And so this gives us a lot of potential for future research, in particular in the shortwave bands, if we can, say, use this information on the phase difference of two identical antennas somehow for say, scientific purposes or studies of the propagation conditions or the like. But what you can do nevertheless with very low effort is now use this phase difference for superposition of the signals. And if you do that, you get the following spectrograms. What you see here are now the spectrograms of every station that has been detected here in the spectrum. For every circular marker here, we see the corresponding spectrogram over time. Yeah, you can somehow guess that there has been some continuous wave transmission, in particular the fourth one here, the fourth station at 7010.6 kilohertz. This looks somehow interesting. And you see also that the received signals from the different antennas look, different, of course, from the combined one. And if you now, the combined one is obtained when you add these stations individually with the corrected amplitude and phase. And on my last slide, which will be the next slide, content-wise, I will show you how this will look like then in time domain. And this is how demodulating this particular station looks like in time domain. We have the signal of antenna 1 on the top. We have the signal of antenna 2 in the middle. And now the only thing I did was estimate the phase shift and the scaling factor between these two signals. I read it from the plot. I just read magnitude and phase from this diagram here. And then I used this correction factor to add these two signals coherently. And what you see down there is here the resulting signal. And you see that the SNR has increased significantly just by adding two replicas of the same signal, and not even, say, separated very largely spatially. Yeah, so it's just two antennas only a meter apart or something like that. And just by adding these two signals coherently, you can get this significant increase of SNR. And this should suffice for my talk today as a teaser for you to maybe look into multi-antenna systems in the future more thoroughly. Yeah, so multi-antenna systems, the ones who see my first talk know that multi-antenna systems are a big thing in communication technology, in particular mobile communications. But to my confusion, or say it's curious that it hasn't been that extensively been used in amateur radio. Of course, there are some activities, and of course, every phased array and every antenna array is a multiple antenna systems. But maybe this talk will lead some of you, to maybe think of using multiple antenna systems in amateur radio applications. Just for fun, because just to find out what are the gains, can you learn something about the propagation conditions, for instance. And I would like, and if I was able to awake some interest in some of you, then I've achieved everything I wanted to achieve with this talk. So this ends my talks, and I thank you very much for your attention. And of course, I will happily answer any questions in the Q&A session.
So Henning, thank you very much for this super interesting talk on a homebrew SDR, which is amazing, as Marcus Miller said in the chat. Yeah, this is really very interesting. I see that you've been exchanging some thoughts before here in the chat. There was a question about passive radar. We have 2 minutes left. Maybe you can give some comments about passive radar. And the clocking architecture question is also interesting, since this entire block is going to be about homebrew things. But I'm going to raise the question later in the panel again. So please, can you say something a little bit about passive radar?
Yes.
What can you do with that?
You can actually do ranging of sources. For instance, think of backscatter things. There was some years ago a nice, I guess it was a press release about a company that used passive radar to detect stealth fighters just using broadcast signals. So, for instance, if you observe the phase information of broadcast signals, radio, TV, whatever, and if you have a large enough bandwidth to collect several transmitter locations simultaneously, so it receives the signals from different transmitter locations, then you can use the phase information of your different receive antennas to detect the presence of scatterers, for instance, of these signals. And this is something that I would find very interesting. And this is why my VHF receiver has a local oscillator input and output, so you can, in theory, build several of those, daisy chain them, and then build like whatever 4 or 8 antenna system receiving in the VHF band. And then if you put the antennas in a circular array, for instance, you get a very nice detection, basically passive radar system that's able to locate the position of scatterers. This is something for the, say, the far goal of what I would like to achieve one day.
That's awesome. Fantastic. Very, very interesting. So I'm actually waiting for your next talk here. Well, you're going to give a talk anyway, again here in
tomorrow. There will
tomorrow. Yes.
That will be on my background in what I did in university back in the day using self-built radio hardware.
Excellent. That's good. Perfect. So there was one other question about clocking, but I reserved a question for the panel. In the meantime, I welcome Leonardo Cardoso here with us. Leonardo is representing, together with Jean-Michel Fried, the European GNU Radio Days. And we're going to have the panel then together. And Leonardo is also going to raise some questions then. So,
clocking was the topic, I guess. Actually, it's very simple. I use a single output channel of an SI5351, a clock synthesizer. And this is the only clock that's used by the ADC. And it's also fed into the SOC, and means I can use arbitrary sampling frequencies. And of course, the receiver has to know the sampling frequency, the piece of PC hardware. But it's a very simple solution, and the ADC uses a double data rate interface, means you get words on both edges of the clock signal. So I and Q are just multiplexed on the edges of the clock, and it's a very nice solution. And of course, if you would daisy chain this system into more channels, you would have to use the same clock on all the boards, of course, to have coherent sampling. But this is not a big problem.
Is there any delay you're noticing? Or is it just clocking signal in, clocking signal out?
Just this the clock synthesizer is just feeding the signal, and actually the delay is not as large as that it would lead to any problems. So basically just hook up the synthesizer chip to the ADC and the SOC, and the edges are somehow matching. Yeah, so we have the edges of the clock are somehow on the right position to ensure proper sampling of the word. This is different to the HEC-RF. I had much more problems with the HEC-RF to get the timing right. I had to insert extra inverters, chains of inverters, to provide proper delay to ensure proper sample and hold times. But the Zinc design is really much less problematic than the HEC-RF design was.
Okay. So very basically, well, I mean, I've never built such a system as you did. So excuse me for raising stupid questions. And the clocking is really actually quite interesting because I think 1 nanosecond of delay would be equal to about 30 centimeters of distance. So if you're working with a nanosecond, that's a gigahertz. But okay, in this case, the clock is probably 10 megahertz, right?
Yeah, so it's 40 megahertz is the maximum clock of the ADC is running at. Yeah, of course, you would need some kind of calibration, yes? So means in the end, when you have built your multiple antenna system, then you would really have to perform some kind of absolute phase calibration, because there are, of course, phase differences, and if you daisy chain your demodulator boards, of course, there is always a slight offset in phase. So we had exactly the same problem with our demonstrator back in university. You have to calibrate this, means you get a different phase angle for each channel, and you have to apply this correction in the end when you do the ranging. You need to do that, yes, because for instance, in particular, we were using 2.4 gigahertz band back then. Yes, of course, every centimeter hurts your little, really. Yeah, so if you don't make the cables painfully equal in length, this will, of course, lead you to problems. And actually, we did a publication back then, back in 2008 or 9. Where we try to calibrate our 8-channel multiple antenna receiver in order to be more precise in ranging. That is a problem, of course. You're right. This was not a stupid question. It is indeed a problem when you have, say, more than 2 channels, basically.
Yeah, and the more channels you have, the more difficulties you have. And I remember a little experiment a couple of years ago where somebody took RTL SDR sticks and interconnected he unsoldered the quarters from all of them except from one, and then interconnected the quarters, or the quartz frequency connection. And that was also quite an interesting experiment, but I've also read on some websites that the results were not just as perfect as theory would have suggested. So handling clocking is an interesting topic, and it can give you some distorted results, deviating from what you really expected in the first place.
Right. Problem is, in that
if I may just squeeze in,
yeah.
Just wanted to show off as we're talking about clocking. Actually, right behind me, we have one of these White Rabbit synchronization systems, and this is being assembled actually for long range the DOA. So in the example that you're following, you have your local antennas, and in this experiment, we're trying to distribute the antennas on a multi-100-meter baseline for high resolution DOA analysis. And I think this is actually quite close to your discussions, as you were just saying, that you have indeed 1 nanosecond will be a phase offset at any radio frequency signal. Here the White Rabbit will give you 60 picosecond standard deviation synchronization on long range base. So that's a kind of topic, and I'm very much interested in your development, because I see that indeed I can put one of these boards that you're developing at the end of the White Rabbit network. So that's quite amazing what you're doing here.
Okay, thank you. What I wanted to mention with these RTL SDRs is if you use the same clock crystal signal, problem is you have these PLLs inside the chip, so you cannot guarantee how the PLL will lock, and you will be maybe synchronous, okay, frequency synchronous, that's nice, but you won't be phase synchronous. So this is why I'm using these ADRF chips, which have a dedicated LO, local oscillator input and output. And that will mean you can directly feed the LO output from one board into the LO input of the other board. So that means you will have some, I guess, some deterministic phase between these two demodulators. Of course, you will nevertheless still have to calibrate it, because you don't know the absolute phase, but you know it will be constant. So at least that's something.
Okay.
And I will add the issue of PLL dithering, where they have included the high resolution frequency steps by dithering, which is awful for phase synchronization, because the phase condition will just keep on jumping randomly due to the dithering effect.
Yeah, so usually integer PLL whenever possible.
Exactly, yes.
Let me briefly interrupt here. I'm just hearing from our studio colleagues behind me that we have a continuous audio problem. We have to fix that a little later. I would rather suggest in that case that we have the panel right now and extend it a little. So, Leonardo, can you say a couple of words about yourself, and maybe then perhaps you also have some interesting experiences with clocking and quartzing and all those funny things. Please go ahead.
Yes. Thank you, Marcus. So I am Leonardo from France. I am an associate professor at INSA de Lyon, and I'm also a researcher at INRIA. And unfortunately, this is way out of my field. Of course, I understand a little bit about the problem. The problem is well known. I think everyone who worked with SDRs and who has ever thought about synchronizing multiple antennas, which is definitely my case, has come across these kinds of problems with synchronization and clocking and everything. I'm actually very interested by the solutions of Paul. Especially, Paul, you were talking about the slight delays that will happen in between any multiple receiver system. And would you rather do the correction of these delays between all these PLLs inside of the FPGA itself, or or rather, let's say a dedicated circuitry, or would you just leave it like this and then try to correct it in software afterwards?
So I personally would always prefer to correct it then in software at the latest possible point in the signal processing chain. But that's just personal preference.
And why is that? Why would you? I mean, if you know that your circuitry has this deterministic delays, why not try to correct at least a little bit of it already in hardware, and then keep the software for the fine tuning?
Yeah, you could do that something. Yeah. I'm not very emotional about this problem. So of course you can just place say a complex multiplier block in your signal chain in the FPGA, and then if you have the multipliers, still spare multipliers, you can do that. Yeah. So, but of course, if you already if you have maxed out your FPGA capabilities, of course, then you need to do it then in software, or you could also do it. No, you need to do it in software on the host processor. To do it in software on the ZOC would be, I don't know if that could be feasible. Yeah, because you could use the Neon extensions from the ARM processor or something like that. But I don't know where this would lead to, how much effort this would be then. So if you have the possibility to do it in the FPGA, okay. And then otherwise do it on the receiving end then.
So I'm also curious. So no, go ahead, please finish.
If you want to build a standalone appliance that just has a little display, it's the, for instance, what I've also done is I hooked up a little TFT screen to my Zynq evaluation board, and I have also USB controller, so we could use, for instance, USB keyboard and use a standalone device, for instance. Yeah? So using a little 3-inch graphical display or something like that. Then, of course, you would need to do it on the system itself. Yeah.
Yeah, I'm also so I fully understand these problems with the FPGA and the spacing that you have inside of the FPGA to add up more signal processing things. I'm curious about that because this is things that interest me nowadays. How much space do you have left in the FPGA? Could we do something with it?
There is some space left, and you have these different types of cells. You have these DSP cells, which can do multiplication, addition, something like that. You have lookup tables, you have RAM, and currently, I guess, if I remember correctly, like about 60% is the maximum utilization of any of these kind of cells currently, but it's the small Zynq. It's the 7010. Of course, you could upgrade to a 7020 Zynq or something like that, or 7035, and then you could do even more stuff in the in the FPGA, in the programmable part, actually. So there's something left. Of course, I could use a different decimator, for instance. Use then different decimation than 8, for instance. I was thinking about buying one of these more expensive ADC chips and do like something 80 megahertz of sampling rate, and then I would need a decimation of 16 additionally maybe, and then I could tune to different to more frequencies, for instance. Then I would need more FPGA resources in that case.
Yeah, it's I completely understand this. I've been working with GNU Radio for a long time now. It's been 2008, 2009, something like that, and I've seen people trying to create SDRs for a long time as well. Just a disclaimer: I was for around 2008, actually 2009, 2010. I worked a little bit with a guy here in France that was trying to create an SDR, which was cheaper and everything. It was called SDR for All. I'm not sure if you heard about it. And the thing about so I know about creating SDRs, and I agree with Marcus Mueller here in the chat. It is a very complicated thing, and seeing your presentation it makes you think that it's so simple. So how hard? I mean, how much has it evolved from, let's say, 2010, 2011 to today, for someone like someone who has some knowledge, of course, of electronics, to get up and do a project like this? I mean, how hard is it today? You said in your presentation a lot, standing on the shoulders of giants, and I thought that was very interesting, because it's true. I mean, in the beginning, it was very hard to have all these things that we have nowadays. But I mean, if I wanted to make my own, how hard would it be?
Hard to answer that question, because my daytime job is I'm a hardware developer. So a lot of the knowledge I used in the project I gained in my daytime job. So yeah, it is. If you have, problem is you need several disciplines. You need analog design, you need FPGA hardware design, and you need software, because you need to write all these ugly kernel modules and the like. And I'm amateur in all of these areas somehow, but basically everything I did was just modifying existing code. So let it be the schematic of the HackRF, or let it be the block design of the Pluto SDR, or let it be the source code of the kernel modules that Analog Devices already wrote for their peripherals. It's not, I can't tell how hard it is. So I'm sorry, I'm too biased to answer that question. But
I did notice that you're heavily using some of these evaluation boards from Analog Device, and I think this makes a big difference to gain access to some of these radio frequency chips without having to assemble some of the most complex radio frequency boards. Of course, they're not cheap, but at least they're readily available, and I'm not sure they were that readily available a long time ago.
Actually, I built them myself because I was too cheap to spend like 400 euros on an Analog Device evaluation board. So I took the schematics from the evaluation boards. You can download them on the Analog website. And then I copied that stuff into KiCad, and then I made a very cheap 2-layer board. It's horrible. That's why I found out that I should at least go to 4 layers if you ever do RF design. So a ground plane is nice, really nice to have in RF. So really just copying stuff. Yeah, and even so, I used the standard application nodes from these modulator chips, and I copied them, and then I added like an analog driver stage for my IQ outputs, a fully differential analog amplifier to be able to drive my ADC, and that's it basically. I plan to put the design somewhere also on my GitHub. So the source code for the kernel modules is already there, and also for the GNU Radio blocks. I also plan to put the block design of the FPGA as well as the demodulator boards onto my GitHub, so everyone can have a look. It's awful. My schematics always look awful because I don't care to make them nice. So you can't expect there are always right angles. There'll also be diagonal wires going all through the board and something like that, or through the schematic, not through the board. Usually I'm quite careful about the layout, but the schematics look awful usually. Yeah, it was basically a process. Yeah, when you look at my talk that I have tomorrow, so I started in university with all this hardware design stuff and building software-defined radios and the like, and I learned a lot from my colleagues also, and I used these kind of hardware, and I learned where the drawbacks were, and I copied stuff that was good. And yeah, that's how it evolved. Yeah, in today's talk, you saw the first board was a Raspberry Pi based thing, non-real-time system, and then the evolution towards this real-time capable system. Then Yeah, so
We have a
part of it is
question.
autodidactic. Yeah.
Sorry. Go ahead, Marcus.
Thank you. We have a question from the chat, and I also remember that Michael Hartier mentioned that. By the way, he just wrote me that he would be off for a couple of minutes, but returning soon. So in Michael's project, yeah, here you are again. Now the palm tree is waving in the background again, so very good. Yeah, well, Michael mentioned a couple of years ago, well, I don't remember when that was, but recently when he was experimenting with enums, but also with the Whisper project, together with the Red Pitaya boards. He made some analysis on power supplies. So when you're using cheap Chinese switching power supplies, these plug-type power supplies, they're leaving which are leaving away all parts of electromagnetic in flux protection and coils and whatever. They're leaving away all those devices for money reasons, for the lower price. Did you have any? Did you make any experiences with DC-DC converters and their influence on your schematics, and how influential were they? I mean, practically no board can do without DC-DC converters.
Yeah, so in the beginning, I powered my analog part also from the USB. That is a problem, of course, because even if you do filtering with ferrite beads and capacitors, you always somehow still get all the noise from the PC, from your PC power supply into your circuit. So this is why I moved to a different approach. I guess you saw it also on the slides. I still use an off-the-shelf wall mount power supply, 7.5 volts, but I have heavy filtering after that. I have a common mode choke, I have capacitors and inductors quite a lot, and I use a linear regulator after that to generate the 5 volts for the evaluation board, as well as 5.5 volts for the analog demodulator board. So it's really quite an effort, and it helps. Yeah, it helps definitely. Of course, the bottom 100 kilohertz, from 0 to 100 kilohertz, are still noisy somehow, but I don't get any nasty spectral lines at higher frequencies. So that actually works quite well. But don't ever try to power your SDR from USB only. Like the Pluto does, or like the HackRF does, it's awful. Yeah, so you use an external power supply whenever possible.
Okay, well, that's a good recommendation. I have some information right now. Adrian, we're still having some problems with the audio, but we're going to solve that, and we're going to play your contribution tomorrow in front of the other contributions, but so that's not in vain, and we're going to get that fixed. So anyway, that was a very, very interesting discussion, and thanks for helping me out to bridge this little gap with some very valuable content and valuable recommendations for everyone who's thinking about building his own SDR architecture. And in fact, we've had these experiments again and again, and successful experiments here in the SCRA. And at the very beginning, I remember Delta Bravo 1 Charlie Charlie, who started with such a board a couple of years ago. And of course, it makes a lot of sense to reuse existing designs, and I mean, why reinventing the wheel if you can do so quite easily? But it is really very remarkable when you just take a sample schematic from an application sheet and put it into KiCad and just produce your own PCBs. That's really cool, very, very cool, and should be a good recommendation to everyone who is thinking about being active and trying to do things yourself. And so we see it's worthwhile, and you can indeed have success by doing it. So that's really the good news from it. Okay, very good. I can hear from my studio colleagues that our next speaker is here. So Adrian, we're going to communicate outside of this channel, and we're going to plan your talk tomorrow at 12:30. So dear audience, please be prepared for a change of program. Tomorrow we're not going to start at 13 hours, but 12:30 with the talk of Adrian Muschak on a GNU Linux multimode SDR transceiver application using GNU Radio and having voice over IP functionality. So this will be an extension actually to this block about building your own SDR application system, whatever this domain of having a transmitter receiver system will contain. So I'm very looking forward to hear your talk tomorrow then.